let's talk of another force. This is the more complicated force, at least conceptually, because there are a few things here that are a little different from what we expect from our common day experiences. Now, there are two types of friction. What we call static friction, that's when the surfaces are not rubbing against each other. Whenever we have two objects, for example, if I have a ramp and I put a block on it and it does not slide up or down, then what kind of friction do we have? It is static friction, no motion friction. And then there is what we call kinetic friction. Quite often we call it also slide-in friction. That's the same example. If I have something like this and the block is sliding, we have slide-in friction. Now, what's interesting, like for the normal force, the value for the static friction is not going to take a unique value. Okay, it's a little bit easier where we have an expression. Okay, and let's describe this. Let's explain the expression. The expression says the static friction force is smaller or equal to a certain mu times the normal force. Okay, let's try to understand what that means. What that means is, one of the things that means is the static friction force has a maximum value, but it can go from 0 up to that maximum value. It does not have a unique value. That's one item. Now the other thing, the Fn tells us the static friction force is going to depend on the contact force between both surfaces. When two surfaces are in contact, they exert forces on each other. And the bigger that force is, the bigger the friction force. The bigger the normal force, the bigger the friction force. And that makes sense. Now, for example, I'm sure you have tried it. If you are trying to pull on something or to get something to slide against the floor, if someone decides to come and sit on it while you are trying to slide it against the floor, it's going to become harder to get it to slide. That's because we are going to have a larger static friction force. Now the mu is what we call coefficient of static friction. Of friction. Let's write it of friction in general. So we'll use mu, the symbol, the Greek letter mu, to refer to the coefficients of friction. When we write mu sub s, then we are referring to the coefficient of static friction. Now, you'll notice here, when we have kinetic friction, we have a very similar equation, except we don't have an inequality sign, we have an equal sign, and instead of mu s, we have mu k. This is the coefficient of kinetic friction, while the top one is the coefficient of static friction. Generally, mu s is larger than mu k. Generally, not always. Generally, they are different, with mu s larger than mu k. Now, what does mu s mean? What does the coefficient of friction mean? It is a quantity that is determined empirically, that's determined by people performing experiments on the surfaces. We cannot calculate it, we cannot predict it very easily. The physics is very complicated to try to predict the value for that. But that's a quantity. Mu is a quantity that's going to depend on both surfaces. It's going to depend on their makeup, What kind of materials are they made up of? Are they two pieces of plastic against each other? Are they a plastic against glass, plastic against wood, wood against, I don't know, whatever. The makeup of these two surfaces, what are they made up of? That's part of what comes into play when we talk of mu. In addition to that, the physical structure of those surfaces. Are they smooth? Are they rough? That's going to play a role as well. Now, and you need to be careful, rough does not always mean that mu is larger. You have noticed quite often you put two pieces of glass against each other, and you'll have a hard time getting them off each other. That's a very smooth surface against a very smooth surface, and we still have a huge coefficient of friction. Okay, so the key here is, what I'm trying to say here, mu is a quantity that's measured experimentally, and it's very difficult to predict, especially at this level, what type of mu we will have whenever we have two surfaces rubbing against each other. Now, the force itself is going to depend on how hard the surfaces push against each other, and that's measured through F sub n, the normal force. And for static friction, it's going to be always less than or equal to that large value. Okay, remember, and I'm going to go through it again now for just 1 second. Remember what we did while pushing on that cabinet. There was no static friction initially. It was zero. And the more I increased my applied force, the bigger F sub s got. There was no unbalanced force on that cabinet until the force I applied became equal to mu s times F sub n. The minute I applied a force larger than that, then there is no more static friction anymore. My object starts sliding. If it starts sliding, we move into this mode here. Whenever two surfaces slide against each other, we don't have static friction anymore. We have kinetic friction or slide-in friction. Okay, that's an easier one to deal with. It is mu k times F sub n. It's very much similar equation, except we have an equal sign. We can exactly calculate it. But there is another important thing. Kinetic friction is always opposite to the direction of motion. That's not the case with static friction. Static friction, to find its direction, we have to apply Newton's second law of motion. We have to figure out how's everything. Now, in that example that we have with the cabinet, it's going to be difficult to show it for sure, but in other cases, it can be easy to figure out that the static friction force is not always it's not always opposite to the direction of motion. Okay, let me give you, before going to the simulation again for a little bit, let me give a couple of examples. If you are skiing, for example, what kind of friction do you have? It is slide-in friction. Okay, whenever you ski, you have slide-in friction. Okay. Now, while walking, what kind of friction? Okay, and that's a little difficult for people to realize. When we walk, it is a static friction. What do? You notice if it is a wet floor, you are going to be able to fall very easy. That's because we don't have enough static friction to hold you. What do you do when you walk? You push against the floor. And you cannot do that pushing unless there is a static friction force. You push against the floor, and the floor pushes you forward. You are able to move forward because the floor moves you forward. The floor pushes you forward. Okay, that's a little tricky concept. What is the force that enables you to walk forward? It is the static friction force between your shoes and the floor. That's why if there is no friction, if the floor is wet, you are not going to be able to walk. We walk because we push against the floor, and as a reaction to our push, the floor will push us forward. I'll give you an example that can convince you of that, hopefully. Try to put a piece of paper, stand over it, or try to kind of do it like if you are going to run, with a piece of paper below your shoes. And get moving as fast as you can. And you notice the piece of paper flying off. Why would the piece of paper fly off? Because your feet pushed it back. And as a reaction to that, and we'll be talking more about that later on, the floor pushes you forward, enabling you to accelerate forward. Okay? So that's a little tricky concept. I can give you another example. Take the case of a spinning disc, whatever type of spinning disc, and place something on top of it. Now, because it is spinning, we know that whatever you are going to put on it, if it does not fall, it must be accelerating. Why is it accelerating? Because the direction of its velocity is changing. It's not staying the same. The direction of its velocity as time progresses is changing. At one time it's pointing this way, at one time it's pointing this way, this way, this way. So what holds it on top of that disk? It is a static friction force. Now, what's the direction of that static friction force? In this case, we'll get back to that later on, actually it points towards the center of the disk. Let me take another example. A wheel, bicycle wheel, car wheel. What kind of friction do you have? Again, it is static friction. An example, I hope you didn't experience it, but if you experienced it, if you are stuck in mud, there was no static friction there. Your car got nowhere. It is the static friction that's going to enable your car to move forward. When you press on the brake, then you stop your wheels from spinning. Then when you stop your wheels from spinning, okay, now if we consider a wheel, then the bottom of the wheel here is going to slide against the road. Then we have sliding friction. But if it is rolling, at no moment do we have a part of the wheel sliding against the floor. If we don't have two surfaces sliding against each other, we have static friction. Now, modern brakes, most of our cars now, most of the newer cars, when you brake, it tries not to lock the wheel. It tries to allow it to lock for a second and unlock. Lock for a short time and then unlock. Lock for a short time and unlock. Why do they do that? Because of this. Because the coefficient of static friction is larger than the coefficient of kinetic friction.